This video is part 2 of the mechanism video, and this is going to discuss the rate determining step in a multi-step reaction. So we're on this part of the note packet, and we will cover the rest of these mechanism notes in this video. Alright, so before we start, I always start this discussion, and some of you are familiar with this discussion because I've used it before, of a non-chemistry example which involves a silly discussion, but a silly example of getting ice cream. And so my discussion starts with talking about that our entire class is going to go to Dairy Queen to get ice cream, but there's one rule, and that one rule is nobody can order or eat their ice cream until all of us get there. So it doesn't seem like it would be a problem. Everybody gets in their car, goes to Dairy Queen, and everybody gets their ice cream. But the issue is that one of our classmates is on crutches, let's say. Okay, so it takes that person a whole lot longer to get to Dairy Queen. So what we are now figuring out is that some of us are going to get to Dairy Queen much faster than somebody else. And so in this situation, there would be a slow person and there would be fast people, right, in getting to Dairy Queen. But if the rule is that we can't get our ice cream until everybody gets there, then we are being hindered, so to speak, by that slow person, okay? So that slow person determines how fast we get ice cream. Okay, so, and again, this is silly, but it paints a picture in your head. So the only way that we can get ice cream faster is if we get that slow person to Dairy Queen faster. So to increase our rate, so to speak, right, to increase how fast we get ice cream, we need to increase the speed of the slow person, right? Think about it. Getting the rest of us there faster won't help the situation at all because the rule still stands. We can't get ice cream until everybody is there. So getting the rest of us there doesn't help our situation. But if we can increase the speed of that slow person, then we can get ice cream faster. And so this is the idea that in a mechanism, so now we're kind of gonna cross the line into chemistry, so to speak, that in a mechanism, there is normally one step that is much slower than the others. Okay, just like our person on crutches. And that slow step is referred to as the rate determining step of the reaction, because it's that slow step that's going to hinder how quickly the overall reaction can take place, just like our ice cream example. Okay. Let me do this first. Okay, so we've related this silly ice cream example to a mechanism by saying that in all mechanisms, there's always going to be one step that's slower than the others. It will be called the slow step. And that slow step is going to be called the rate determining step because it's going to influence the overall rate. Okay? Now, if you look at your note paper, you have kind of a bullet point that says that there are specifically two situations. And those two situations are, and I'm not going to write this because it's listed right on your paper, but we're talking about right here. These two situations are, the first one is a mechanism with a slow first step or initial step. And that idea is fairly straightforward. We'll talk about it briefly, and I think it will make sense to most of us. The second example, though, is a mechanism where the first step is the fast step. And so that means the slow step would be like the second step of the mechanism, okay? And in that situation, determining the rate for the overall reaction is a bit more complex, and it involves a little bit of a derivation of some kind of big ideas, and then deriving the rate for the overall mechanism. So we're going to do an example of both of these. But first, underneath kind of this bullet point in that little space, I think what I want you to write is this, because it's a takeaway. In either one of these cases, okay, whether it's the fast first step or the slow first step, the rate determining step, which we said was the slow one, governs, how did I say this? Governs the rate law for the entire reaction. Okay, so this is a big takeaway. In either case, no matter which one we're talking about, the rate determining step or the slow step is going to govern the rate law for the entire reaction. And we're going to see that in just a minute when we do these two specific examples. Okay, so the first one we're going to do is the one that's fairly straightforward, which is the slow initial step. And your paper already has this written out. It says consider a mechanism, and we have, let's see, step 1, step 2, this is the slow step, and then we have this, and this is the fast step. Okay, so this is on your paper. So, okay, so we've already learned previous to this that we can take these two steps of the mechanism and add them up to get the overall reaction. So NO3 would cancel, I have an NO2 that would cancel, and my overall reaction would be NO2 plus CO yields NO plus CO2. And what we're really looking for is this. Okay, what's the rate law for this new reaction? Okay, now, we know that this first step is elementary and this second step is elementary, right? That's part of the, let me get a marker. That's part of the rules with mechanism. So we can write a rate law for each of those steps if you want to. The rate law for the first step would be K times the concentration of NO2 squared. Remember, if it's elementary, the rate law comes solely from the stoich, right? And in the second step, which I don't have any room over here for, so let me just say, okay, in the second step, the rate would be equal to the concentration of NO3 times the concentration of CO. Okay, and again, because it's coming from the pure stoich of the reaction. Okay, now, so first, some kind of background information. So NO3 is an intermediate, okay? Why is it an intermediate? Well, because it fits a description of an intermediate, that it's produced and then consumed, okay? So it's made in the first step and it's used up in the second step. So it's an intermediate that is produced slowly in step 1. Right? Why? Well, because it's the slow step, okay? And then it's used immediately in step 2 because it's fast. Okay, so NO3 is an intermediate. It's produced slowly in step 1, okay? So it's slow to be produced, but then as soon as it's produced, it's used in step 2 because step 2 is the fast step, okay? So in this case, my first step is the slow step. It's the rate determining step. And let me write this. So step 1 is rate determining. And therefore, the rate law of step 1 is going to equal the rate law of the entire reaction. Okay, and it's as simple as that. So the rate law of my, do I have enough room at the bottom? Yes. So the rate law of my entire reaction is going to be equal to the rate law for my first step, because it's the slow step, and it is affecting how fast the rate is going to occur for this overall reaction. Okay, so we're kind of dependent upon how quickly the NO3 is produced in the first step and then used up in the second step. So it's step one that's slowing us down, and the whole mechanism is going to have a rate law consistent with the rate law of the slow step, which is going to be this. Okay, notice your NO3 is not present in the rate law. Wait, is that what I wanted to say? No, I'm sorry. Your concentration of CO, I'm sorry, this guy. Your carbon monoxide is not present in the rate law, even though it's a reactant, and that's because it follows in a step that's faster, and then therefore does not affect the rate, so to speak, because it's not rate determining, okay? So these are the ones, the slow initial step are the ones that are fairly easy to understand, and not a huge deal. If you remember back to right here where I had written the slow initial step mechanisms are fairly straightforward. It's the next one that is a little bit more roundabout, so to speak. Okay, so the next one is, what about if we have a fast initial step? And you have a couple bullet points, so I'm not going to write them, I'll just read them to you. And so, let me get my papers here. Okay, so mechanisms with a fast initial step. I have said this. It's possible to derive the rate law for a mechanism in which an intermediate in a reactant is in the rate determining step. So that seems odd to us. Why would an intermediate be in the rate determining step? And it says that this happens when the first step of a mechanism is fast. Okay, so consider they give us a reaction. They say it's different than the one we just looked at, and that's because we needed one with a fast initial step. And so they give us two steps of this mechanism. And they say maybe in this first reaction, this happens, which is fast. And then in the second, this happens, which is slow. Okay, of course we can cancel some things out. This thing will cancel. Oh, I'm sorry. Oh my gosh, no. Jeez. They're both reactants. Sorry. They don't cancel. The only thing that cancels is this. Whew, my bad. And so it gives me 2NO plus Br2, making 2NO-Br. Of course, that matches this. And of course, we are interested in determining the rate law for the whole reaction. Okay, so now this one's different. I have a fast first step. So something I need to draw your attention to, which is not on your paper because I couldn't make it work, is that this first reaction is actually a reversible reaction, okay? And this comes up much later in the equilibrium chapter. But this first reaction means it can proceed in both directions. So the NO and the Br2 can make NO-Br2, and then the NO-Br2 can break down to remake these two things, okay? So reversible reaction. So we're going to label a couple things. We're going to label this top arrow as K1. That's the rate constant of step 1. This one's going to be K2. It's the rate constant of step 2. And then I'm going to label this going the opposite way as K-1, okay, only to mean reverse. And that's how your book does it too if you were to look this up in a textbook. All right, so how much room do I have? A little bit. Okay, so step 1 involves both a forward and a reverse reaction. Okay, so that's interesting. We haven't seen that so far. And then, of course, we have step 2 is the slow step, which is rate determining. Now, we could write a rate law. Okay, we could write a rate law for step 2, which is fine because it's an elementary reaction. So I could say rate is equal to K2, right, times the concentration of NOBr, 2 times the concentration of NO. And we could say that that's my rate law. However, the thing that should bother us a little bit is that there's an intermediate in this rate law. And we don't normally see, or maybe I should say ever, that's a 2, sorry. We don't see intermediates in rate laws. So we have a goal, and that goal is to express step 2's rate law without the intermediate. Okay. So, my goal is to express this rate law, but I need to get the intermediate out of it. And so this is where it becomes interesting, and it becomes a discussion of a derivation. Okay, so I'm going to erase this because I am totally out of room, and I need more room to proceed. So let's write a couple of things. Let's write that step 2's, I'm only writing this so we know what we had. Rate law looked like this. And I'm trying to express this without this component in there. Okay, kind of rearranged. So, we're going to talk a little bit about step 1, which was the reversible step. And hold on, let me make sure I copy it down correctly. Okay, so we have this first step, which is the production of the intermediate, and it's fast. Okay, so if you can think about this, this is like these two things collide together very quickly and form this. But step 2 was slow. So we have this huge accumulation of the intermediate sitting and waiting for it to be used up in step 2. See, this is totally reverse of what we just talked about a little bit ago, where the intermediate was used immediately. In this case, it's being formed very quickly, but then it's being used later very slowly. So it accumulates. Okay, there's a whole lot of this intermediate. So we have a couple assumptions to think about. And that is the fact that this intermediate can either do one of two things. Okay, it can either move forward into step 2, which I do not have written, but you can look at your paper. It can move forward into step 2 and react via the step 2 process, but remember, that's slow. Or it can fall apart, so the reverse of this first reaction, and recreate the Br2 and the NO. Okay, so it can either proceed via step 2, or it can kind of fall back apart to make the NO and the Br2. So, because step 2 is slow, we're going to make an assumption that most of it falls apart. Okay, as it's waiting, so to speak, which means that the NOBr2 would form this, which is the reverse of step 1. Okay. So, we keep having these continuing ideas. So because step 2 is so slow, the forward and the reverse step 1 occur much faster than step 2. And they actually establish an equilibrium. Where their rates are equal, or their speeds, okay? So the forward and the reverse reaction, so meaning this and this reacting to form this, and then this falling apart to make this and this are actually occurring at the same time, and they actually establish an equilibrium in which their rates are equal to each other. So, I'm going to erase this, but I still want to leave our reaction up here. Okay, so the rate of the forward is going to be equal to the rate of the reverse. Now, keep in mind, this is an elementary reaction, so I could write the rate law of the forward reaction using just the stoich. It would look like this. It would be K times the concentration of NO, or I should call it K1, sorry, because it's the forward. K1 times the concentration of NO and the concentration of Br2. See, that's the rate of the forward reaction, okay? And we're saying that's going to be equal to the rate of the reverse reaction, which would be K in the reverse times the concentration of NOBr2. And these are equal to each other because, see, this is the rate of the forward and the rate of the reverse. Okay, and I know this is a little bit intense, okay? But the AP test has been known to ask this question, so it's definitely worth us attempting to discuss it. So, now, we're kind of like, who cares? I got this far, but what's the deal? Remember the goal. The goal was, we know this is the rate determining step and the rate determining rate law, but we want this intermediate concentration out of there. So we're going to use this relationship and solve for this, okay, concentration of the intermediate, and then plug that value into the rate law. And we're going to do it like this. Look how close I am to having the concentration of NOBr by itself. K is in my way. So I'm going to divide both sides by K of the reverse. Whoops. Okay, and I get that the concentration of NOBr2 is equal to K1 times the concentration of NO over the concentration of Br2 over K of the reverse. Now, this is a mess. I'm going to substitute this value in for this, because see, this is equal to this, and there I have this. So I can substitute that in. Okay, now, how do I do this without losing my whole paper here? So we're going to say that the rate is equal to K2. See, that didn't go anywhere. Now this thing is equal to this. So here comes the mess. Times K1 over the concentration of NO times the concentration of Br2. Woof! All divided by K to the negative first. Oh, and I forgot something. Sorry. I forgot this NO. See? Oh my goodness. So now, can we reduce this a little bit? Yes, we can. NO times NO is NO squared. Br2 is still there. Now there's a discussion of what the heck do I do with this? Okay, what is this? K of the second step times K of the first step over K of the reverse. Okay, where what is said is that K of the entire mechanism is going to be equal to K2 times K1 over K to the negative 1. And so we just end up calling this K. And so this is the rate law for that mechanism that we saw. Let me find my paper. Right here. Okay. Now, what's interesting is you might look at this and say, wait a minute, but that rate law, there it is, right, doesn't match the first step. Nope. It's close, right? But it doesn't, because it would be NO to the first. And it most definitely doesn't match the second step. And that's because the second step was the slow step, and we had to derive this rate law based on the fact that that intermediate was accumulating after the first reaction had happened, and therefore had to be dealt with in an equilibrium type situation. So again, this I told you on the first page, this way is much more challenging. It's definitely a derivation of the rate law, okay, of the mechanism, and most of the time you're going to see the first one, which was the slow step, is first, and it's super simple. But this has been on AP tests in the past, and it's definitely worth us discussing and worth us, finding a practice problem and talking about.